So let's continue our discussion on linear regression. I hope to finish it today. And the idea is that, well, so we have already seen what the vanilla linear regression looks like, right? And we have also looked at, okay, what are the issues with linear regression? And then we looked at one way to control, well, so we also looked at Bayesian linear regression, which is also very important, where we put a prior on your weight vector, and we learned with that. And then we also talked about this need to control the complexity of linear regression, right? In the context of simple linear regression, where x is x and then you're trying to do y is equal to w transpose x, the notion of complexity is not very clear. But then we looked at, okay, how to do this basis function expansion, which allows us to actually do nonlinear regression by converting our vector x into a nonlinear form by application of multiple basis functions, right? And somebody asked me last time after the class that what should these nonlinear functions be? And the good thing is that they can be anything, okay? So you have some input, your raw input, which is x, right? And x itself might be, let's say, 4-dimensional. You might have 4 different features or attributes for your data. Now you can apply any type of function on that. So you can apply functions on each one of these 4 dimensions, or you can take 2 of them and do some nonlinear combination of those. You could do anything. But the whole idea is that from x, you move to this new dimensional space, which is p, by applying p basis functions. So there is no real sanctity about what type of basis functions these should be. They could be anything. I mean, you would expect them to be nonlinear, otherwise you won't get the nonlinear form, right? So if you just simply take x and convert it to 4 times x, you'll still get a line. But if you convert it into x squared, x cubed, or any nonlinear function of x, then you hope to get a nonlinear curve, right? So one form, which is, now as I said, right, so there is no constraint on what type of nonlinear function these could be, but of course, then it becomes our burden to choose these, right? But one simple way is to just apply these polynomial expansion, where you replace x by x to the power 0, 1, 2, all the way through p. That's what you will do for your programming assignment as well, the last problem. But what we saw last time in one of our workbooks was that by changing that p, like how far you want to go in your expansion, you can learn really nonlinear functions, right? So in fact, I was showing you this last time. Maybe we'll go through it again. So again, remember, so we have some data which looks like this. Well, then first thing what I do is I do not do any nonlinear expansion. So let's say this is my data, right? So first thing what I do is I do not do any nonlinear expansion, and I get a line, right, which is fine. This is our linear regression. So inside it, it either does a least squares formulation or it does a like a MLE thing, right? But now, if I change my degree, which is my expansion, you will see that it becomes more and more complex. So 2, it becomes a quadratic curve, 3, a cubic curve, and as you grow it farther, right, so let's say we go to 20, what you will see now is it actually pretty much fits the data perfectly. So the training error is 0. So if you are doing sort of your least squares close to 0, there's still something, but you can still go further up. And at some point, you'll see that it does a perfect job here, right? So by this time, it has expanded your x into a 35-degree polynomial, and then fit a curve there. And when we put it back, so what happens is that you have changed your x to a 35-degree vector, right? Now, when you do linear regression, you're still doing linear regression. The weight that you're getting are getting linearly combined with these feature values. But then when you bring it back to your original space, the line will look like a curve, and you'll see that it fits the data beautifully. But we know, as machine learning students, is that this is not good, right? This is a classic case of overfitting, which means that this will have really poor generalizability. Right? So how do we control this? So we do need some nonlinear behavior, but we do not want it to be too nonlinear. right? And we have seen this in neural networks as well. Is one way to do that is this notion of regularization, where we try to control the complexity of your solution. In this case, your solution is W, weight vector. We try to control its complexity. And one way to control its complexity is to control the size of the magnitude of the values, right? So you have d values. If you have weight vector d values, we want to control the magnitude, right? So this is what we know, what we call the notion of regularization. And this is a general concept. This is not focused only on linear regression, right? So the idea is that you have any machine learning algorithm where you're trying to learn these weights, which are not weights, but parameters of this model, which are all encapsulated in this theta, then you do want to maximize or minimize the quality of your solution. So this could be error or likelihood, but you also want to control the complexity, and the complexity is stored in this r of theta. So there's some function that defines the complexity of your solution, and you want to minimize that, right? And the lambda is the parameter that controls the impact of either one. So if lambda is low, then you want solutions that fit training data more. Lambda is high, you prefer more simpler solutions. You're okay in accommodating some error, right? So in linear models, it turns out that, of course, in linear models, what will happen is that you always have a weight vector, right? So linear regression is one form of linear model, but we will see many more, like we have seen perceptrons, right? All of them have a weight vector. And one way to control the regularization, or one way to do the regularization, is by controlling the magnitude of your vector. So let's go into this discussion a little bit. All right, I don't have my usual sheets today. So the idea is that we want to control the norm of the vector, right? So in geometry, you must have come across the notion of a norm. So if you have a vector in a two-dimensional space, right? If you have this point, right? So this is W is equal to W1 comma W2. The norm of this vector is basically the length of this vector, right? And you must have seen this notion of Euclidean norm, where the Euclidean norm is written as W2 square, right? So basically, the idea is that you have a vector and you're converting it into a number, because that's easy to work with. So this is what we call Euclidean norm. But in general, there is this notion of LP norms, where if you have a vector, you can define this LP norm. And Aaron, when you were in my office, I think I gave you a slightly wrong definition. So pay close attention. So if you have any vector, the LP norm is defined as W1 to the power P plus W2 to the power P. So let's say this vector has D elements, 1 over P, right? So what you will see is that the Euclidean norm is essentially L2 norm. So this is actually same as an L2 norm, right? But you can also define an L3 norm, which will be W1 cube plus W2 cube by 3. So you'll come across these norms a lot in machine learning. So that's one another L3 norm, but it's defined as this. There's also this notion of L infinity norm, which is slightly special. So because you can't do raised to infinity, so this is actually just max of W1, W2, W3. And in different settings, you'll see different of these norms are useful. All right. There's also this notion of which we'll actually look at today is L1 norm, which technically should just be summation of all of these. But what you do is you take the absolute values. So this is the L1 norm, right? All of them, the effect of norm is that they're converting a vector into a value, right? So one way to do regularization is to try to control the norm, right? And one typical way is to control the L2 norm, because L2 norm is easier to work with, and I'll show you why. So regularizing linear model. So this could be more than just linear regression. The idea is that you have some j of w, which is your objective function, plus you do L2 norm of w. So you can another thing I forgot to tell you is that you can express mathematically or denote a norm as this. So LP norm is also denoted as these two straight bars and then P. So P indicates what norm it is, right? In the case of norm, oftentimes you will also see L1 norm. This should be technically written as this, but you'll also see it written as just absolute of W. Okay, so that's just notation. In the case of one way of regularizing is to normalize the square of the L2 norm. All right, so this is known as L2 regularization. Why do we do square? Is because it's easy to compute the gradient of or the derivative with respect to W when it's a square, and we'll come across that very soon. So in the case of linear regression, right? In the case of linear regression, your loss function is like this. So n data points plus lambda. So this is the L2 regularization for linear regression, and this has a special name. This we call ridge regression. So ridge regression is nothing but L2 norm regularization of linear regression. All right. So the first thing we are going to see is, okay, how do we find W? So now our objective function has changed a little bit. So this is our objective function, a function of W, and we want to find the W that minimizes this whole thing, not just, so in the case of least squares, we just looked at this, right? So what is J of W? What is W that minimizes this part? Now we want to minimize the sum, because that lets us sort of control the magnitude of W. Because what will happen is, if you look at this equation closely, is that if there is a solution which gives very small error, but this W, the magnitude is high, then it won't prefer that. It will try to prefer simpler solution, which connects to the notion of these squiggly lines that we saw. So if I reduce the W, the magnitude or the norm of W, what you will see is that line will start becoming simpler and simpler. It might still be nonlinear, but it would be simpler than if you don't do any regularization. So that's the effect, right? So it controls the overfit. So let's quickly look at, okay, how do we do this? Now, sort of this part already, how to derive this, right? Now we are going to also include this. So one way to also write this is just a side discussion, is this is the L2 norm. L2 norm can also be written as W transpose W, right? All you're doing is you are taking each element of this vector right here, and then you're squaring it and then adding it up, right? We're not doing a square root because that's the square of the L2 norm. So this can be written as W transpose W. Okay, so now how do we optimize for this? That's easy, right? So you compute djw by dw, and then we set it to 0, and then solve for w, and you get your answer. Another thing you can do is that you can just compute the derivative, which will be the gradient, and feed it to the minimizer, right? So in your programming assignment for part 3, you will do this straightforward, computing the derivative, setting it to 0, and solving for w. Whereas for part 4, you will compute the gradient, just the derivative, and then feed it to the minimizer. But what you will see is it will give you the same answers. All right. So now quickly, let's see how to do this. I want to do the whole of this again, right? Because we did this for the general unregularized regression. So, but just to give you a feeling, I'm going to write it as this. This we have discussed before, right? This summation can also be written in matrix form as this, plus lambda W transpose W. And one thing that in the programming assignment, you will see, I also have some constants here, half or something, right? So what will happen is that, I mean, you'll have to be a little careful. You can't just take this expression and assume that is the answer, right? It depends on what is your objective function. So if your objective function is this, then you can use whatever I provide in the notes. But if your objective function has a half here, or 1 by 3, or 1 by n, right, your objective function will change a little bit, but it's going to be very similar. It's just the constant will change a little bit, right? So sometimes you'll see a half here. You usually put a half here because when we do the derivative, there's 2 that gets cancelled out, and life is, I guess. Anyway, so what we do is we compute the djw by dw, which will essentially be, if you remember it right, you can think of this as a whole vector. I'm going to do a slightly different way. You can think of this whole thing as a vector, right? So you can say it is 2 times. So remember, if you have any vector and you have d by dx, so if you're computing the dot product of a vector with respect to the vector itself, it is 2x. Okay, so in this case, it will be 2 times y minus xw, and then we'll take the derivative of this with respect to w. This doesn't depend on that, so it will be minus x, right? So this will be, so actually the x will come here. And when you go back, you can sort of check it out, but it's that. And then this is again the same thing, right? This is 2 times lambda w. Let's transpose it. Right. So I just want to make sure all the dimensions match. And then, so this will be then all the 2's go away. Actually, then you set it to 0, right? So you set this. Set this to 0. And then essentially you say minus 2x transpose y minus x. The 2 disappears. That's why usually people are 2 here, so that it's half here, so that it goes away beforehand, but it doesn't matter. And then essentially the idea is that the w that you'll get when you rearrange these will look like this. It will be x transpose x plus lambda I inverse x transpose y. Very similar to what for linear regression, except that we have this new term. I is an identity matrix. The reason we have an identity matrix here is because lambda is a scalar value. This is going to be a d cross d. So you want identity matrix so that you can add two things together. All right, so this is the solution that you get out of this whole thing. All right. The reason we could do this so easily is because we had this quantity here, because it was an L2, right? Computing the derivative of an L2 norm with respect to W is easy. It's just 2 times W, right? But if you have something else, so instead of L2 norm, if you had L3 norm, then things become a little more tricky, right? So that is why it's just like a ease of computation than anything else, is that we tend to use L2 norm, because when you take derivative L2 norm, you get the linear form. Right? So that is the idea. Any questions so far? Yes.
I found that lambda j equals to 0. We also derivative the systematic equation of lambda without using the partial derivative of the j.
You're saying you can do that?
Yeah. Just lambda j equals to 0.
Oh, you're saying just set j equal to 0? If you set j equal, so the question is why do we set this equal to 0? Why not set j equal to 0? Is that what you're saying?
Yeah.
I don't think you'll get the same result, because I mean this is basically a simple mathematical optimization, right? So you have a function of w and you're trying to find the w that minimizes this whole thing. We are not trying to find w which solves this equation, which makes this equal to 0, because I don't think you'll get a w that will set this to 0, because this quantity is a positive quantity, right? W transpose W is always positive, right? So unless W is all zeros, you will never be, and this is also positive quantity. So you're adding 2 positive quantities together. So if you set it to 0, the only solution that you'll get is when W is all zeros. You see what I mean? So, I mean, try to think of this from a standard optimization perspective. You have a mathematical objective function of W, and you want to find W that minimizes this. We don't want to find W that sets it to 0. Well, that will be nice if that is 0, right? But you can't get that. I mean, yeah, go ahead.
You can get same result, but I just don't understand why.
No, what I'm saying is I don't think you'll get the same result. Would you? Because, see, my point is, and this is your objective function, right? If you set this to 0, the only solution of this would be when W is all zeros, right? Because if you think of this quantity, this part is a positive quantity, right? And this part is a positive quantity, right? So the only value solution for W that will make this whole thing equal to 0 is when this is 0 and you get somehow you get this to be. This will only happen if all your data points are on a line. Then you get a W that will set to 0. But if they're not on the line, then you cannot get the solution, right? See, let's go back to simple curve fitting. In a curve fitting example, if you have some 3 data points, right, you want to fit a line to that, right? You can, in this case, find the W by setting it to 0, because there is a solution, right? But if you have a situation like this, in which you cannot draw a line, but you want to find the, which would be maybe this, then you cannot get this by setting that quantity to 0. You'll have to optimize for it. So that will give you the closure. But we can talk offline again if that's not clear. All right? Any other questions? All right. So we did ridge regression. All right, perfect. So ridge regression is nice. We like it. It's also known as Tikhonov regression because it was proposed by Tikhonov, I guess. So this is the solution, right? I'm sorry. Just give me a second. It's not the mapist. Well, maybe I didn't change it. Well, this is just a ridge estimate, not map. This is this plus x transpose y. This is exactly what I derived, right? Now, what you will remember is that in last class, we also did this map estimate where we put a Gaussian prior on W. And there also we got a very similar result, right? If you, let me go back here. Remember when we put a map prior on W, a Gaussian prior on W with a covariance matrix in which everything was tau square, right? So it's an identity matrix multiplied by a scalar. So it's essentially a diagonal matrix. When we compute the map estimate, then also the mean of that W is exactly like what you get from ridge regression, except that instead of lambda, here you have sigma square tau square, right? So you get the same solution. So that's the beauty of it, right? So basically ridge regression is just equivalent to setting a prior on your W. And I kind of went over that last time as well. So remember, when you're putting this zero mean prior on W in Bayesian regression, essentially what you're saying is that my prior belief is that my W is at the origin, which means that my W has all 0 values. And my data is telling me that W should be here. So the map estimate kind of brings them together, right? And that tau square kind of controls how much it comes towards origin. And here also the same story. There's this lambda which tries to force it towards 0. So if I set this lambda to, let's say, very high, 20,000, right? What will happen is that because this lambda is so high, your optimization will completely ignore this effect, right? And it will find a solution in which W is all zeros, because that's the one that will give you the minimum error. So the same idea. So ridge regression is equivalent to Bayesian regression's map estimate when your prior is a Gaussian, okay? Because that's also important. We always assume that prior is a Gaussian, but there's no real reason to do that. You can assume any other prior as well. But for ridge regression, Gaussian prior Bayesian regression is the same, all right? Any questions? All right, so that leads me to the next. Oh, okay, before that, all right. So one good property of ridge regression. So now let's see what ridge regression does, right? How does it work in real world? So here it is, right? So the same idea. Now what I do here is that I do the same thing. I plot a function which is nonlinear, and I generate some data, and then I do my polynomial basis expansion. But now I apply ridge regression to that, right? So I'm actually using sklearn's ridge regression, which you're not allowed to do for your assignment, but inside the same thing happens, right? So let's see what happens now. So this is what happens. So this was your data, right? This is if I just plot a line, linear regression. This is if I go to the power d and apply linear regression there, no regularization, that is this, degree 10. And this is when you apply a 10 level polynomial expansion, but you also do ridge regression on that, all right? So now what you see is that the solution is still nonlinear, but it's not as complicated as unregularized one, right? And you can control the amount of this by controlling this alpha parameter. So for example, if I said alpha is basically lambda, so it will become a little more nonlinear. And one question that might be in your mind is, how do we set alpha? And the answer is that there is no principled way to do that. So this is again very similar to what you did in neural networks, is that you try out different values of alpha or lambda and see the one that gives you the best answer. All right, any questions so far? Okay, now another good thing that ridge regression does is that it also helps you control the impact of correlated variables. So this is another issue with linear regression. So in your data, right, if you have bunch of variables or features, let's say 10, right, and if two features are very correlated, they are almost the same, right, then regression gets confused, and I'll show you how it gets confused. So the idea is, and the point is that ridge regression helps you control that. So the problem of correlated variables. Right. So let's say you have some data which is like this. Y is W naught. Let's say you already know how it was generated. So W naught plus W1 X1. Right? This is good. Now have data that is generated by this. So let's say I took this line and did some noise to it and I got some data out of it. Now I fit my linear regression to this. Then if you have enough data, it will tend to recover these weights. It will find out what the actual equation was, right? Linear regression is good at that, as long as it's all linear. But what if I add another dimension to this, another variable, and I say that y is W naught plus W1 X1 plus W2 X2, where X2 is actually very close to X1. So X2 and X1 are the same, let's say, right? So I just added a dummy variable to my data set, which is just a copy of your other one. Plus, let's say we add some noise to it so that it doesn't become perfectly correlated. Otherwise, linear regression won't work, right? You won't be able to compute the inverse. But let's say X2 and X1 are highly correlated. Now, what is the solution that you would get, right? Because you could get a solution. What will linear regression do? It could learn W naught plus 2 W1 X1 plus 0 X2, right? Or it could learn W naught plus W1 X1 plus W2 X2, or it could learn W naught plus 0 X1 plus 2 W2 X2, because all of them are correct, right? Because almost the same answer, right? And depending on how much noise you add here, what you will see is that linear regression will do different things. Sometimes it might learn this, sometimes it might learn this, sometimes it might learn this. So it gets confused with this correlated features. What you want is for it to always give you the same answer, right? So that is an issue with linear regression called the problem of correlated variables. So now let's just sort of see that first. Any questions so far? Okay. All right, so here it is. So this is another new experiment here, right? So what I do here is that I create a data set, right, in which I have 3 features. And I assume that all of my features are just random. So there are 3 different features. And then what I do is I create my y by, so y is basically the first feature just by itself, plus 2 times the second feature, plus some random noise, right? So this is how I create my data. And if I now fit linear regression to it, this is the solution that I get. So let's look at this. So this is the intercept, so this is fine, right? This is close to 1, and that is almost close to what we used here, right? So we used almost 1 times x1, so it learns close to that. This is 2 times x2, so that's also good, right? And the third one gets ignored because we don't actually use third one in generating y. So think of this as our generative model, right? So we already knew what our w was, and we just did that w transpose x, added some noise to it here, and then we got our y's, right? Now we are trying to recover it. So it does a pretty good job. It recovers all the important features, and it ignores the one that is not very important, right? That's good. But now let's see what happens if we add some correlated variables. So here what I do is, in each loop, what happens is that this is my x, raw x, and then here I generate 3 features which are basically the same feature with some noise added to it. So I'm basically adding 3 dummy features, right? And then I add my y, right? So y is nothing but 3 features and some noise added to it, but each one of these 3 features is actually the same feature with some noise added to them, right? Then I fit my linear regression, and I do it in loop. Now what happens here is, what you will see is that the solution kind of varies all over the place. So sometimes the weight associated with x1 is negative 0.178, sometimes 0.753, sometimes actually 1.2, sometimes close to 2, right? So it gets confused a lot because of this. The reason it is changing in each loop is because every time I'm adding a different noise, right? And that's what you would expect in real world as well, is that you have some generative process and then some corruption to that. And based on the corruption, your linear model becomes very unstable. So the reason I call this model very unstable is because in every run, it is giving very different results. So for example, here, right, the weight of x3 is almost 0, whereas here the weight of x3 is close to 3, right? So that is the issue with linear regression. And as I said on the slide, is that ridge regression actually helps you control that. So I'll quickly show that to you. So what happens if I fit a ridge regression here with some alpha, excuse me. Ever since I changed from Python 2 to Python 3, the life has been miserable. Oh, here it is, right? So now what you see is that the model is relatively stable. The values are not fluctuating too much. They're still fluctuating, but not too much. And if I keep changing my alpha, you'll see slowly it kind of becomes very stable. So now it is basically, in every run, it is giving very similar values. So the point is that linear ridge regression helps you in 2 ways. One is that it controls the overfitting, which we have seen here. Plus, it also helps us deal with this notion of correlated variables. All right? Any questions? This is the end of ridge regression. Okay, good. So now, the next topic we're going to look at is, what if we use a different type of regularizer? So we have looked at L2 norm here, right? So that's called L2 regularizer or ridge regression. But what if instead of this we use something else? So one that is very popular is in which we use L1 norm, right? That's called a, so this part is still the same. You still have an objective function, which is your squared error loss, right? But here, instead of a L2 loss, now I have a L1 loss, all right? And this has interesting properties, and this actually is more popular than ridge regression, and I'll tell you why. This came out in 1996 from Stanford. You know, you must have seen the book by Tipshirani and Hasty. So those were the guys who proposed this method. So it was called least absolute shrinkage and selection operator, or also known as LASSO. Right? So LASSO is again a general concept. So it is applicable to any machine learning algorithm. The point is that instead of trying to regularize the L2 node, you try to regularize on the L1 node, right? And the formulation is the same, and you can say, hey, it's easy to solve for this because I can compute the gradient, set it to 0 and get my answer, or compute the gradient and feed it to a minimizer and get my answer. But the problem is this quantity over here, right? So this is a mod, right? This is a summation of the mod. So it is very hard to compute the derivative or the gradient of a modulus function, because the modulus function is not smooth, right? So if you look at, let's say W has only one quantity, one element inside. So the modulus function will look like this, right? If this is W, any Wi, so it will always be greater than 0. So this is mod of Wi. The problem is that 0, the derivative is not defined, because if you're coming from this side, it's going to be this way. If you're coming from this side, it's going to be that way. So it's not easy to, it's not straightforward to just apply the same sort of gradient descent or setting the derivative to 0 to solve the lasso, right? But there are other ways to do that. That is not part of this course. But it's a big field by itself, is how do we find solutions to this kind of problem, right? So there is no one solution, there are many. And if you're interested, you come back to my office hours, we can discuss more about that. But in this class, what we'll assume is that this is the expression for lasso, right? And there are ways to solve this, right? But we'll not go to that, all right? But one thing that lasso does is, why is lasso so popular, right? So it does the overfitting issue, but at the same time, it also helps you do feature selection, all right? So if in your problem, you have many variables, right? Many features, and some of them are useful, some of them are not. Lasso lets you select only the useful one. So it is doing both things together, controlling the overfitting issue, so regularizing it, because that's the effect of this, right? You're, again, in terms of the regularization, it has kind of similar effect as ridge, because you are trying to penalize solutions in which the absolute values are very high. But because of this mod, what it does is that it favors solutions in which there are lots of zeros and only a few non-zero values, which essentially means that it's kind of doing feature selection for you. So the weights, so if you do ridge regression versus lasso, what you will see is that in ridge regression, it tries to make everything small, or the weights, all the weights tend to be smaller. Whereas in lasso, what it does is that it makes some weights to be 0 and some would be non-zero. So it tries to do this shrinkage. That's why the name is shrinkage, right? I like to think of it as a lasso. You just lasso your variables, bring some of them down. That's my interpretation. But I want to show the effect of that. So here's lasso, right? Lasso, again, the lasso in sklearn. If you look at the source code, you will see how they solve it. But the idea is the same, that what happened? I think X needs to come from here. Let's see, right. So lasso has the same effect as ridge in terms of regularizing it. It's also making things sort of smoother, right? And there is an alpha parameter with lasso as well, which is over here. So if you change it, you can control it more. Right. So that is the effect of lasso. But the other beautiful part of lasso is that it helps you induce sparsity. When I say sparsity, it basically means that when you have the weight vector, only some of them are non-zero, everything else is 0. And that is kind of what we'd want to do if you are doing feature selection, right? So if you run lasso on some data set, it will give you a weight vector, right? And when you see that, hey, a lot of these are 0, which means that these were not useful. So you can use it for feature selection right there. So for that, I'm using a standard data set. This is a Boston data set that we looked at a long time back. So this data essentially has, some information about prices of houses. So each row in this data set is some attributes about houses, and what you want to predict is its value by looking at the attributes. Okay, so these are all houses in Boston. So when you fit linear regression to that, this is what you get, right? So this is a linear regression model, and these are the names of different attributes in different features. So don't worry about what these names are. What we are more concerned with is these values. So this is the weight vector essentially. This is the intercept term or the bias term. This is the first weight value, so on and everything. What you see with linear regression is that everything has some value attached to it, right? Because linear regression does not do automatic feature selection, but it is known that this data has some feature which are not useful. So when you do lasso on that, you will see that a lot of these features, the weights have become zero. They have been shrunk to zero because these were useless features from the lasso's perspective, right? So not only did it improve the quality of your model, because if you look at the cross-validation error, that is lower than, in this case it's almost the same, but slightly lower. But it's better than doing just linear regression, but it also helps you do a little bit of feature selection, because now you can look at this weight vector and say, hey, indus and age and rad and tax, these are useless parameters because lasso says that the weight for them is zero. So think about this idea, right? So you have this weight vector. If some values are zero, basically when you're doing y is equal to w transpose x, 0 is getting multiplied with the corresponding x value, which means that feature value is never being used to compute y. So that's why we call it useless. So if you look at it like this, right? So this is what you get from lasso. So these are the weights. So in this data set, there were 13 features. So you have 13 weights, right? And then these are the weight values that you get. And what you see in lasso, which is the green one, is that a lot of times you will see a zero value, which means that it sort of let you ignore some of this. And this effect is more pronounced in other data sets where you have more unwanted values. So if you added something like ridge regression to this, you might see some interesting results as well. So for example, here, if I make it ridge with alpha equal to whatever, then the answer is slightly different. And if I plot it here, then what you'll see is that the ridge tries to put everything small, whereas lasso tries to make few of them zero and few non-zero. All right? Any questions? Well, alpha is lambda. In sklearn, I don't know why, but they use alpha for that. All right, so going back. Now, we saw that ridge regression is equivalent to Bayesian regression when your prior is Gaussian, right? It turns out that lasso also has a counterpart in Bayesian regression. So, but the only difference is that there, the prior that you set to your W is no longer Gaussian, because Gaussian gives you a ridge. Instead of Gaussian distribution, if you use this distribution, which I don't think we have talked about, is Laplace distribution, named after famous Laplace, is if you use this as the prior on W, right? And then you compute the posterior for W given your data, then the solution that you get there is same as lasso. And you can see why, right? So if you look at Laplace distribution, it has a very similar form as Gaussian, except that it has two parameters, mu and b, right? Very similar, but instead of a square term here, in Gaussian you have this x minus mu transpose inverse of a sigma x minus mu, right? That's how it works. Here, instead of that, you have a L1 norm of a difference between W and mu, right? So this you can see corresponds to this, right? In the case of ridge regression, there's a square term because you're doing L2 norm, and that corresponds to the square term inside the exponent of the Gaussian. Here, this mod connects to this. So you can do Bayesian regression with a Laplace prior, and that will be same as doing lasso, all right? And the reason they are the same is because if you look at the Laplace prior, right? Somewhere I had that. Yeah. Let's not talk about student today. Aha. So this is the PDF of a Gaussian, the black line, and this red one is the PDF of a lasso, right? Oh, sorry, PDF of Laplace distribution, right? What you see is they have very similar form because both of them have exp raised to something, right? So the form is similar, but this Laplace tends to be more narrow and sharp, right? So it rises up very sharply and then it dies out very quickly. So in statistics, they say this notion of fat tail versus not so fat tail. So it turns out that Gaussian has a fat tail. What does that mean is that even when you go far away from the mean, it still gives you some density, right? It doesn't become zero very fast. So it keeps on going and then it dies out. Whereas Laplace kind of dies out very fast. So that it's very high in the at the mean, of course, but then it goes down and then sharply drops off, right? And that is the reason why Laplace will give you more sparser solution. Why? Because it would prefer solutions in which if anything is not zero, the penalty. See, the reason ridge and also this Gaussian prior gives you solution in which everything is small is that if you let anything to be large, any W component to be large, the penalty that you pay is W square, right? So that's why it has to put everything small. In the case of Laplace or Lasso, the penalty that you pay for anything that is large is not very high. So it rather prefers to make some of them absolutely zero and some of them non-zero. So I mean, this is something that's not part of this course really. So if you want to know more, we can talk outside. But this is sort of just to give you an idea of what is the difference between Laplace and Gaussian, right? Now this also has, now somebody can ask us that, okay, when we did lasso, which is on the top, because of this modulus sign, it is very hard to do the gradient, right? What if we go the other way? We do the probabilistic way where we try to compute the posterior. But it turns out that there also you will have problems because now this prior is no longer a conjugate of your likelihood, right? Which means that the posterior will no longer be Laplace again. Posterior will be something else. You can solve it, right? But it will need a lot of mathematical trickery, all right? But there are solutions. So the thing to take back from this discussion is that lasso and Bayesian regression with Laplace prior are equivalent. Any questions? Very nice. All right. And then, okay, so then people talk about, okay, when to use lasso, when to use ridge, and I talked about that, right? So ridge lets you ignore the impact of correlated variables, whereas lasso lets you select variables, right? Both of them have some nice properties. Both of them control overfitting, of course. Now, of course, in machine learning, this happens a lot. So if you have two good things, then you typically tend to put them together and say, let's use both, right? And that's what is called elastic net regularization, in which you have a lasso term over here and a ridge regression term over here. So you do both. It gets best of both worlds. Of course, then you have to specify lambda and 1 minus lambda and so on. Again, because of this modulus term, you cannot simply compute the derivative, so you have to apply something else. But there are solutions. So elastic net is sort of like a balance between the two. All right, what's the time? All right, I think we can stop here. There's one small discussion I want to have before we move to logistic regression, but I think it's better to have it on Friday morning, and then we'll talk about something else, which is kind of extension of this. Any questions so far? All right, so I'll see you on Friday. Thank you very much.